Welcome to the video lecture series for Texas A&M University course Math 150. Today we will look at section 2.6, Graphing Rational Functions. I will take a look at some additional chapter 2 problems and the graphs of the rational functions, question number 21. You can find the accompanying handouts at bit.ly/RayleneMath150. Let's begin. We can start off with the graph of y equals x over x, but that's a basic function, so I'm going to leave this one, and if we have time we can come back to it. I'll start off then with part B, 3x minus 3 over x plus 2. I'm going to refer to the function as f of x, and we want to express the function both in the original, probably expanded, improper fraction form. I'll write that under here. Expanded improper is likely how the function will be given, but not always. And we can write it in factored and, if possibly, reduced. Factored, reduced, and still improper form. And we can also write the function in proper fraction form. So to do that, we go back to the expanded form and we do some long division. We can either do long division or synthetic division, and in this example, because we have a linear denominator, we can do synthetic division. So I'm going to do the synthetic division. And know that we can rewrite this function as 3 minus a remainder of 9 over the denominator of x plus 2. So from these different forms, we can get different elements or characteristics or features of the rational function. So I'm just going to move this off to the side, make it a little bit smaller. And now let's begin analyzing. We have several steps, and the first step we're going to do perform all steps on the reduced fraction. We can't reduce here, so it's all the same. Okay, so the first step is the coordinates of any wholes. As we know, a whole occurs when an x value makes y indeterminate, or in other words, whenever we have a common factor in the numerator and the denominator. So we are looking for the common factor to be equal to 0. In this case, there's no common factor, therefore there are no wholes. The second thing we want to look for are the X-Intercepts, and we get the X-Intercepts by setting y equal to 0, which is equivalent to saying that the numerator only is equal to 0. And in this case, the numerator equal to 0 tells us that x is equal to 1. And so that comes from the factored form. And as an ordered pair, we have an x-intercept at 1, 0. The third thing we are going to look for is a vertical asymptote. And a vertical asymptote is an x value that makes y approach positive or negative infinity. In other words, to be undefined. So let's just be clear. The x-coordinate of a whole makes y indeterminate. And in this case, there is no x value that makes y indeterminate. An x-intercept is an x value that makes y defined to be 0. And a vertical asymptote is an x value that makes y undefined. And when a fraction is undefined, that means that the numerator is non-zero and the denominator only is 0. We say the word only because if we have both numerator and denominator equal to 0, then the y value, or the fraction value, is indeterminate. And in this case, we get x is equal to -2. So we have only one domain restriction, and that is x is equal to -2. The fourth step will be to make a sign chart using factors and x values from steps 2 and 3. So for our sign chart, I'm going to build my graph from here, so I'm going to make it fairly large and neat. And so we know that we have an x-intercept at 1 and a y-intercept at -2. So at -2, we do not include the x value. It's not part of the domain. And at x equal to 1, we have an x-intercept and a light boundary line. I'm not going to put the y-axis in just yet because it is not one of the boundaries. Now my factors technically are 3, x minus 1, and x plus 2. And you can put 3 in as a factor if you want. X plus 2 gave me the first root, and x minus 1 gave me the next root. Why don't you pause the video and try getting the sign chart filled in by yourself. Okay, well we know that y equal to 3 is always a constant value of positive 3. So we really don't need to include this line in the sign chart if you don't want. So we may omit or eliminate this line. For the x plus 2, we get negative and then positive and then positive, and x minus 1 is negative, negative, and then positive. So the quotient of these three things we've decided to call f of x, or y, and y in the first region is positive, then negative, then positive. Along with the sign chart, because we are going to take the sign chart one step further and actually draw the graph, we will shade the regions on the sign chart where the function will not lie. Now the next step after finding the sign chart is to come up with the y-intercept, and I think I'll put it here. The y-intercept is the value of x, it's the y value when x is 0. So f of 0 in this case is equal to -3/2. So sorry, I'm just going to write in here in brackets x equals 0, and therefore f of 0 equals -3/2. So we have a point at 0, -3/2. Now this y-intercept is actually a check for our sign chart. Let's go ahead and put the y-axis in now. The y-axis would be along here somewhere. And at y equal to -3/2, it seems to confirm the sign chart because we have not blocked out this region. So this is -1 and this is -2. That's about the y-coordinate. The next thing we want to work out is the equation and type of the non-VA. And the non-VA comes from when we have the quotient. So we need to work out the quotient, which we've done from the proper fraction form. The reason the quotient is going to be the non-vertical asymptote is because the non-vertical asymptote is the graph that the original function looks like when we zoom out. When we zoom out, we're talking about letting x approach positive or negative infinity. And from the proper fraction form, we know that the fraction part, which is improper fraction form, has a certain value that it approaches as x approaches positive infinity or negative infinity. Namely, the denominator is going to get bigger and bigger and bigger in a positive or negative direction. So 9 over bigger and bigger and bigger will approach 0. And as a result, f of x, or the y-coordinates, will approach a height of 3. And 3 is a constant, so we know that we are going to have a horizontal asymptote at y equal to the quotient, which is y equal to 3. So we can go ahead and plot that on the graph. At a height of 3, we have a horizontal asymptote. Now you can go through and take away some of the things on your sign chart, or you can draw your graph in a separate graph and not on top of the sign chart. The seventh step is to find out, does f of x, the original function, intersect the non-vertical asymptote? And so we do that by solving a system y equals f of x and y equals q of x for their intersection points. Now we can express f of x in proper fraction form as quotient of x plus remainder of x over denominator of x. And so what we really want to do is set the two y-coordinates from the function and the non-vertical asymptote equal to each other. So we end up saying that q of x plus r of x over d of x must equal q of x. Then we can subtract the quotient value, which in this case is 3, from both sides. And every time we want to do step number 7, it boils down to us solving r of x over d of x equal to 0. Now we can multiply both sides of this equation by d of x, and so this equation is equivalent to solving a simpler equation. Namely, does the remainder term from proper fraction form have any real zeros? Well, in this case, our remainder is -9. And so we want to know, solve for x such that -9 is equal to 0, and we find no solution. And because this equation has no solution, the remainder has no zeros, so remainder over denominator never equals 0, so the function heights and the non-vertical asymptotes are non-vertical asymptote heights are never equal. Therefore, the function f does not intersect the non-vertical asymptote. So we now have some information, and there's still some more information from calculus that we don't know, and we can't be completely convinced that we have the graph drawn properly until we see that in Calc 1, but we can come up with a fairly good idea of the graph. We know that the function has to pass through these 2 points, and we don't have any holes in the graph as another guiding point. We know as x approaches -2 from the left, y has to approach -infinity from the sign chart. And we also know as x approaches +infinity, as we zoom out on the right end behavior, y must approach a height of 3. And so we get a graph that looks more or less like this. So this is one branch on the right-hand side of the vertical asymptote, which is at x equals -2. We also have a branch on the right side of the vertical asymptote. We don't have any points, but we do know that we will not cross the horizontal asymptote. We do know as x approaches -2 from the left, y must approach +infinity, and we know as x approaches -infinity, y has to approach a height of +3. And so we end up getting a graph that looks more or less like this. And if you wanted to confirm, you can take a couple of x-coordinates and plot the points, and you will see that the graph is never actually going to lie in this region either, because it would require crossing the non-vertical asymptote. And so there we have the graph for part B. Let's take a look at part D, E, and if we have some time, we'll do F. I think for now we'll do parts D and E to get the basic idea of what's going on here. In part D, we've got x cubed minus 1 over x. And I'll call the function again f of x. We should be fairly familiar with the difference of squares, the sum of squares, the difference of cubes, and the sum of cubes special factoring. And so we can factor the difference of cubes as x minus 1 times x squared plus x plus 1, all divided by x. Now we see that we've got a linear times a quadratic over a linear factor. And we want to know if the quadratic, which I'm going to call p of x for now, p for polynomial, if it has any real roots. And so to do that, I'm going to work out its discriminant. The discriminant is b squared minus 4ac, which is going to give me 1 squared minus 4 times 1 times 1. And we get 1 minus 4, which is -3. And because the discriminant is less than 0, therefore p of x has no real roots. As a result, the y-coordinates on this parabola will either only ever be positive or negative. The y-coordinates cannot change sign. So we have to take a look at, in the sign chart, whether or not this will be positive or negative. Well, very quickly we know when x is 0, y is going to be 1, which is positive, and therefore all of the y values will be positive. This is by the intermediate value theorem, which we can discuss at a later point. So we now know that we cannot factor x squared plus x plus 1 any further, and we don't have any common factors, so we're ready to begin our 7 steps. Step 1 is to look for any holes in the graph, and we have no common factors, therefore we have no holes. Step 2 is to get the x-intercepts, in other words, to set the numerator only equal to 0. That only occurs at x equal to 1. Step 3 is to come up with the vertical asymptotes, which is to set the denominator only equal to 0. Because we have no common factors, and the only factor in the denominator is x, we have a vertical asymptote at x equal to 0. Step 4 is a sign chart, which I will do on the next page, but in the meantime, we'll continue on. Step 5 is to get the y-intercept, which means to set x equal to 0. And when we set x equal to 0, you can do it either from the factored form or the expanded form. And in the factored form, we get 0 minus 1, which is negative 1 over 0, which is undefined. So the y-intercept has to be a defined y value, and we are reminded that the whole y-axis, whose equation is x equal to 0, is a vertical asymptote. And the function will not cross the vertical asymptote, so there is no y-intercept. Step 6, we want to find the non-vertical asymptote, which requires the proper fraction form. And when we ask for the non-vertical asymptote, we want both the equation of it and the type: horizontal or constant asymptote, linear or slant asymptote, parabolic or quadratic asymptote, etc. Now we can actually predict the type by looking at the leading terms of the numerator divided by the leading term of the denominator. X cubed divided by x is going to give us x squared, because we keep the base and we subtract the exponents 3 minus 1. So we know we're going to get a quadratic or parabolic asymptote, and what we want to do is come up with the actual quotient, which requires us to put this function into proper fraction form. We're very lucky that we don't have to do long or synthetic division, because there's only a single term in the denominator. And because there's only one term in the denominator, we can actually divide into each of the terms of the numerator. So x cubed over x is equal to x squared, and we get minus 1 over x. So we see that the quotient is actually just x squared. The reason we don't just take the leading term of the top divided by the leading term of the bottom is because we may have other terms from the quadratic, a linear term and a quadratic term, that we would not be getting by simply dividing one term by another term. We would have to do the full division. That said, let's say that the quotient worked out to be x squared plus 3x minus 1. As x approaches plus or minus infinity, which is what happens when we talk about end behavior, this approaches the same thing as x squared. And so these two have the same monomial or simple end behavior. So ultimately the 3x term and the negative 1 do not contribute as much in size as the x squared term does when x approaches positive or negative infinity. So in either case, we have this example gives us y equals x squared as the non-vertical asymptote, and now we want to know if f of x crosses or touches the non-vertical asymptote. Remember, we said in the last example that this ultimately means we want to set the function, which is quotient plus remainder over denominator, equal to the quotient. And when we do that, we really want to find out if the remainder term has any real zeros. So the remainder is negative 1, and does negative 1 ever equal 0? The answer is no. So we have no solution, and therefore there are no intersection points. So from here, we'll do the sign chart, we'll put all of the information together, and we'll draw the graph as accurately as possible without calculus. So here is the x-axis, and the only factors that will contribute to roots are x minus 1 and x. So we have x equal to 0, which is a vertical asymptote, and it also happens to be the y-axis. And we also have x equal to 1, which is the x-intercept. Furthermore, the three factors are given, but x squared plus x plus 1 does not contribute a root. I will just include it so we can see what happens no matter what. So if you wanted to think numerically, you could take a test point in each of the regions. I might take negative 2, I might take 1/2, and I might take 2. And if I substitute negative 2, or in fact any number that is less than 0, I'm going to get 4 minus 2 plus 1, which is a positive number. If I pick negative 1 or anything, this will be positive. Similarly, if I pick a positive 1/2, noticing that these coefficients are all positive coefficients, therefore there's no way for this result to be negative, so this has to be a positive in this region. And furthermore, a positive 2 substituted in with positive coefficients will give us positive. So this x squared plus x plus 1, if if you recall thinking graphically, is at least as high as y equal to 1, and we're going to have no x-intercepts, so we have always positive outputs or heights on this graph. So I like to think graphically as opposed to thinking numerically, and I'm going to remove these from my sign chart and my graph. Okay, in the next region we have x as negative and then positive, positive. There's only one sign change at x equal to 0, and x minus 1 changes sign at x equal to 1, and we have negative before and positive after. Multiplying or dividing these gives us the function f of x, which has a sign in the first region of positive, then negative, and then positive. Noticing that all of the exponents on the factors that contributed roots were odd exponents, we always expect a sign change over the root of each factor. If one of these exponents had been an even number, then over its root there would not be a sign change, according to the table of values in the sign chart. So we are going to draw the graph, so we can go ahead and shade where the graph does not lie, and that can help us to better visualize where the graph will go. Looking back at the rest of the information, we had to plot the x-intercept and the vertical asymptote to make the sign chart, so now we're ready to do steps 5, 6, and 7. We have no y-intercept. We do have a non-vertical asymptote of y equals x squared, and so if we try to sketch this fairly accurately, if this is y equal to 1, then we have a parabolic asymptote that does something like this. And step 7, we don't have any intersection points, so from now we actually have to try to understand what's happening in the graph. When x approaches the vertical asymptote, so if x approaches 0, from the right, y has to approach positive infinity, because we don't have that part of the graph blocked up. From the sign chart, we don't have it shaded, I mean. So this is true, and as x approaches 0 from the left, y has to approach negative infinity. We try not to make the graph curve back around because it would fail the vertical line test. We also know that we have an x-intercept, and we don't know how it's going to go through, but we can pretty well expect that the graph will go smoothly through. So I'm actually just going to try to connect that and make it a little bit smoother. Now when we come here, we are used to seeing the graph flatten out or maybe approach a slant line, but we have to kind of hug the shape of the parabolic asymptote. Maybe it doesn't happen right away, but we don't need to worry about the scale. Similarly, on the other side, remember that this green or parabolic asymptote is actually getting wider and wider and wider. So the red graph, which also has to hug along the green asymptote, is going to do something like this, and we did not find that the red curve of f of x will cross the green asymptote. And so the best that we have is that the graph looks like this. You might ask the question, will the graph lie over here? Well, it won't lie underneath the green asymptote, but the red graph will take on these x values just only when these two, the asymptote and the curve, get higher, because that's when the graph is also going more to the left. So while we don't have graph in this region, these x values on the negative side of the axis are part of the domain. They do produce defined y values on the graph. Okay. So you can take a look at the graphing calculator program if you want to confirm this graph. And by changing the views, the window zoom, we can confirm the non-vertical asymptote. So y equals x squared is the parabolic asymptote, and if we zoom out, we indeed see that the purple asymptote is being hugged. Sorry, the red asymptote, which is now purple, the red asymptote is being hugged by the purple curve. Okay, I'm going to change the curve to red, and I'm going to make the asymptote green, like I did in the picture. Okay, and I'll take a screen snapshot of that so we can see it. Now, we may want to change the window dimensions in the graphing calculator, and we do that by going to Graph, Set 2D Range. Because we are squaring the x values to get the y values, we don't need to go very wide for x before we have gone very high for y. So I'm going to set my 2D range to maybe negative 100 and 100 for x, but then maybe, I don't really need to go very negative for y, but I think I will go up to 1,000 or 10,000 for y. And so if I zoom in just a little bit, I can see that my red curve is actually different, but already the two curves look the same. So if it looks quite green. If I take off the green one, I can see the red one underneath. So changing the window zoom will actually give us a really good idea that the non-vertical asymptote is in fact the shape that our graph has when we zoom out. And by zooming out, I mean that x is approaching positive or negative infinity, but even on this graph, x only had to approach negative 80 or positive 80 before we could fairly clearly see the parabolic asymptote shape. Okay, we're going to take a look at part E, and we'll leave this one as the last one. And I'll try to remember all of the factors as I type it into or copy it into a new slide. So in part E, we had f of x is equal to x minus 2. I know we had a quadratic here. I think it was x squared minus 5x plus 6. And all divided by, let's take a look, x minus 3 times x squared minus 1. So the first thing we want to do is fully factor. It's been partially factored, and of course in 2.5, zeros of polynomials, we can remember how to use the rational root theorem to come up with some possible rational roots and actually fully factor, had this been expanded as x cubed, etc. But I've given it to you partially factored, and we should be able to factor a quadratic reasonably quickly. So we see we get x minus 2 times x minus 2 times x minus 3. And that's all divided by x minus 3 times x plus 1 times x minus 1. And now we actually do have a common factor. So in order to reduce this fraction, we have to carry over the domain restriction. What I mean is, once I write this in factored form and reduced factored form, when we look at the expression, the fraction, there is no domain restriction of x equal to 3. X is allowed to be 3, but in the original function, x was not allowed to be 3. So in order to reduce this and make the reduced fraction equivalent to the original fraction, we must also carry over the domain restriction. It is also true that x can't be negative 1 or positive 1, but we can see that because in the fraction we have those denominators, whereas we can't see by looking at the reduced fraction that x can't be 3. We have one more thing to do, and that is to put the function into proper fraction form. So I'm going to expand this so I can do that. So when I expand this, I'm going to say f of x is x squared minus 4x plus 4 divided by x squared minus 1, and now I need to do long division. So when we divide, we're looking at a ratio of the leading term of the top divided by the leading term of the bottom. So the red boxed x squared divided by x squared is going to be 1. And that 1 is a constant, so let's put it into the constant column. Then we multiply back through, and we get x squared plus 0x minus 1, and we subtract. When we subtract, we see that the x squareds, as they are meant to, let's show that we're subtracting. The x squareds, or the leading terms, cancel. Negative 4x minus 0x is minus 4x, and 4 plus 1 becomes plus 5. So now that the degree of the polynomial resulting here is smaller than the degree of the denominator, we know that we have proper fraction form, and the remainder is negative 4x plus 5. So we can express this fraction in proper fraction form as 1 plus negative 4x plus 5, or 5 minus 4x, just in case you're not sure about the negative signs and who they affect, and x squared minus 1, and we must still carry over the domain restriction. Technically, I should have put it there as well, and I didn't. Okay, so now we are ready to state all of our 7 pieces of information, as well as come up with the sign chart and then put it all together in the graph. It's like a big puzzle. So the first step, working from the reduced function always. Well, technically, we work from the original on step 1. So we look for common factors, and we saw a common factor of x equal to 3, and therefore we have a whole, or let me just say that the common factor, which is x minus 3, set equal to 0, gives us x equal to 3. So therefore there will be a whole located at 3, comma, and then the reduced function evaluated at 3. So when we take 3 and we substitute it into the reduced function, we have a few versions of the reduced function. We have a factored version, we have an expanded version, and we have a proper fraction form version. The most convenient one may be the one that has the least x's, or maybe the one in factored form. I like the factored form. So 3 minus 2 is 1, 1 squared is 1. So 3 plus 1 is 4, and 3 minus 1 is 2. So 4 times 2 is 8, and 1 over 8 gives us the y-coordinate of the whole is equal to 1/8. Recall that the original function and the reduced function are almost completely identical. The only difference is where the original function has a whole, the reduced function has a point. And all we need to do is find out the y-coordinate that the reduced function has to know what the y-coordinate of the whole is for the original. And so the y-coordinate of the reduced function will be 1/8 when x is equal to 3. So the original function has a whole at 3, 1/8. Now the remaining steps we work from the reduced function. Well, technically we were working from the reduced function, it's just we needed to get the x equal to 3 from the original. So step 2, the x-intercepts come from the numerator only, having zeros, and the zeros of the top are x equal to 2 with a multiplicity of 2. You don't need to indicate multiplicity of 2, but it may help you understand the shape of the graph, or whether the x-intercept goes smoothly through, turns around, and is tangent to the x-axis, or flattens before going through. Now the vertical asymptote are zeros of the denominator only, and we have 2 zeros. So we have a vertical asymptote at x equals -1, or at x equal to 1. Step 4 is the sign chart, involving only the x-intercept and vertical asymptote x-coordinates and their factors. Well, I shouldn't say only those factors are involved, but only those factors contribute to the x-coordinates of 2, -1, and 1. The next thing is the y-intercept. The y-intercept we get by setting x equal to 0 from the reduced function, because the original and the reduced are only different at the whole, at x equal to 3. For every other x value, they are the same. I think the expanded reduced version is easy to substitute x into, and we see we get 4/-1, which is a y-intercept at 0, -4. Step 6 is the non-vertical asymptote equation and type. We worked out the proper fraction form, and we saw that the quotient is 1, and the remainder we saw is 5 minus 4x. We already knew the denominator and the numerator. So the quotient is 1, so our non-vertical asymptote is a horizontal asymptote located at y equal to 1. And as far as step 7 is concerned, does f of x intersect q of x? We said that that's equivalent to finding the real roots of the remainder. From proper fraction form, the remainder is -4x plus 5, or 5 minus 4x. And so if we set 5 minus 4x equal to 0, that says that x will equal 5 divided by 4. So therefore, yes, intersection point of the two graphs, the function and the non-vertical asymptote or the horizontal asymptote, or the end behavior asymptote, and the intersection point will be located at 5, 4, and then we can take 5 fourths. We can take 5 fourths and substitute it either into the original function or into the quotient. Well, if you take 5 fourths and substitute it in this version, we get 5 minus 4 times 5/4. 4 times 5 over 4 is 5, and 5 minus 5 is 0. And that makes sense because we had just found a 0 of the root of the remainder. So 0 over non-zero will be 0, and the y-coordinate will be 1. But of course, we could have easily have plugged x equal to 5 over 4 into the quotient function and found that the y-coordinate is 1. So we have an intersection point on the horizontal asymptote at 5/4, 1. So now let's make our sign chart. We have 3 x coordinates to substitute in. We have 2, -1, or 1. X equal to 2 is an X-intercept. However, x equal to 1 or x equal to -1 are vertical asymptotes. And now we're ready to put our factors in. Go to the fully factored form, and it's not enough just to write x minus 2, we have to write x minus 2 all squared. And I'm going to put my factors in order that their roots appeared. You don't have to do this, it just makes this filling into the sign chart a little bit more predictable. And when we fill in the signs, we get negative, positive, positive, positive. And we see that there is a sign change over the root of x equal to -1 because the vertical asymptote has odd multiplicity, much like the graph of the basic vertical asymptote of odd multiplicity. Do you know its equation? It is y equals 1 over x. Similarly, x minus 1 will be negative, then positive, then positive, and there is a sign change, and so we have a vertical asymptote again of multiplicity 1. Because x minus 1 comes from the denominator of the function. It is a vertical asymptote. Then at x equal to 2, we have a parabola, and the parabola has an x-intercept at x equal to 2, and it is concave up. So the y-coordinates, except when x is 2, all the y-coordinates are positive. So the result is of multiplying and dividing these appropriately gives us f of x, or the y-coordinates, and the signs will be positive, then negative, then positive, and then positive. And we know that over x equal to 2, which had the factor of x minus 2 to an even exponent, that we do not expect a sign change. So we can do some shading. We shade below, we shade above, we shade below, and again we shade below. Now we're ready to put in the y-axis. And I make it a little bit longer and I label it with a y. And we can also put in the y-intercept at 0, -4. Hopefully this confirms our sign chart, and it does. If we had made a mistake, we would have to go back and try refactoring and filling in all of the rows of the sign chart more carefully. We have a non-vertical asymptote, which is a horizontal asymptote at y equal to 1. And so we add that to our graph. We know that we have a hole in the graph at 3, 1/8. And when x is 3, y equal to 1/8. Now this arrow may be confusing. I'm going to take it away. When x is 3, y is 1/8, which is approximately at this height. So it's not a point, but it is a guide for the graph because it's a point on the reduced function, but not on the original. We also have, I think I'll use red for my whole graph. We also have another point, namely the point where the function crosses the non-vertical asymptote at 5/4, which is 1 1/4, comma 1. Of course, the height has to be at 1. It has to be on the non-vertical asymptote. Apart from that, we know the same behavior. As x approaches the first vertical asymptote from the left, y must go up. As x approaches the first vertical asymptote from the right, y must go down. I think I said from the right. Coming from the left goes up, coming from the right goes down. Then we have to pass through this point, and as x approaches the second vertical asymptote from the left, y must approach -infinity. Meanwhile, as x approaches the second vertical asymptote from the right, y must go up. And as x approaches -infinity, y must approach a height of 1. As x approaches +infinity, y must approach a height of 1. So these points kind of give us a guide here, And we know that we can't cross the vertical asymptote, so we must be coming up like this. And wanting to go through that point, which is why we have removed it, because x equal to 3 is not in the domain, gives us one branch of the function. With two vertical asymptotes, we will end up with 3 branches, unless you cause or call the separation at the hole another branch. Well, in the middle section, we can see a point, and it may or may not be the maximum height. I don't know if it is. So I'm just going to draw my graph a little more generally and not making any assumptions that my y-intercept is also the absolute maximum, or sorry, the local maximum. It may be, but until we have calculus techniques, we won't know for sure. So I would accept a graph if you had drawn it like this. Similarly, I would accept a graph if you draw it like this. All 3 of those are possibilities. And lastly, we have to talk about the first region to the left of the x equal to -1 vertical asymptote. In this region, we could see maybe coming underneath, but then we would have to cross the non-vertical asymptote, and we found only one point would do that. So we know that we can't have any graph in this region here. And so we must be above. Now, it is possible that this graph does all sorts of funky things, and it wobbles around and changes from increasing to decreasing, but until we have calculus to be able to find some of the local maximum and minimum points, we don't know about that behavior. So for now, we'll keep it as simple as possible, which is that the function is purely increasing, not touching the horizontal asymptote anymore, because we only found one intersection point, and we get a graph that looks something like this. Now, in mathematics, it turns out that very often simple is best, at least for polynomials and rational functions. And so we can confirm our graph using graphing calculator software for the given function. And so our function said, if we go back to the original function as opposed to the reduced, it was given to us as y equals x minus 2 times x squared minus 5x plus 6, all divided by x minus 3 times x squared minus 1. Now I'm going to go back and put my graph range, reset it, and I'm also going to draw my non-vertical asymptote, y equal to 1, and zoom out a little bit. In fact, we noticed that the y-intercept was not the local maximum point, but the version of it was that the local maximum is to the right of the y-intercept. For our purposes in calculus, we don't know that. We also know that there is a hole when x is equal to 3, and we can see that by tracing. When we trace, the graph says that y is not a number. We have not defined y to be one of the infinitely many possibilities coming from the indeterminate case of 0 over 0 when x is 3. And the rest of the graph actually is quite straightforward on the first branch. Of course, it does not cross the non-vertical asymptote because we found only one point to do so. And the point that crosses the non-vertical asymptote does so at 1.25 or 5/4, comma 1. And so we have come up with a fairly accurate graph. The only thing we don't really have accurate is the placement of the local maximum in the middle branch, which is to the right of the y-intercept, not to the left as I had drawn it. So this should really take us through many of the different varieties and types and cases that you might encounter. Consider that graphing rational functions is really like a big puzzle where all of the pieces will confirm and connect to produce only one possible graph. And the only way to get better is to do more practice. This concludes the 2.6 More Graphing of Rational Functions practice. Please make sure you have completed all of the questions and prepared a list of clarifying questions. That's all for now.